Welcome to this exploration of one of the most fascinating discoveries in modern physics. Gravitational waves are ripples in the very fabric of spacetime, produced by some of the most violent and energetic events in the universe. These cosmic disturbances were first detected by the Laser Interferometer Gravitational-Wave Observatory, known as LIGO, opening an entirely new window into understanding our cosmos. In this presentation, we'll uncover what gravitational waves are, how they're created by massive accelerating objects, and how scientists managed to detect these incredibly faint signals from billions of light-years away. Gravitational waves are disturbances in the fabric of spacetime that propagate outward like ripples on a pond. Imagine throwing a stone into still water and watching the ripples spread across the surface. Similarly, when massive objects accelerate in space, they create ripples that spread through spacetime itself. These waves travel at the speed of light through the universe, stretching and compressing space itself as they pass through it. Unlike sound waves or water waves, gravitational waves are distortions of space and time themselves. As they travel, they carry energy away from their source, bringing us information about the most extreme events in the cosmos. In 1916, Albert Einstein made a remarkable prediction as part of his general theory of relativity. Einstein revolutionized our understanding of gravity by proposing that massive objects don't just pull on each other through empty space. Instead, they curve the fabric of spacetime around them. According to his theory, spacetime tells matter how to move, and matter tells spacetime how to curve. Einstein's equations showed that when massive objects accelerate, they should create waves in this curved spacetime. However, these waves would be so incredibly weak that Einstein himself doubted they could ever be detected. It would take nearly 100 years before technology advanced enough to prove him right. Gravitational waves have several unique properties that make them both fascinating and challenging to detect. First, they are extremely weak. Even the most massive cosmic events produce only tiny distortions in spacetime by the time the waves reach Earth. Second, gravitational waves are transverse waves, meaning they oscillate perpendicular to their direction of travel. They come in two polarizations, called plus and cross patterns, which describe how they stretch and compress spacetime. Perhaps most remarkably, gravitational waves pass through matter almost completely unimpeded. Unlike light, which can be blocked by dust or absorbed by matter, gravitational waves travel through anything in their path, carrying pristine information about events that would otherwise be invisible to us. Gravitational waves are produced by massive accelerating objects in the universe. The strongest sources are binary black hole mergers, where two black holes orbit each other at incredible speeds before spiraling together and merging into a single, larger black hole. Binary neutron star mergers are another powerful source. These occur when two ultradense stellar remnants, each containing more mass than our Sun, but compressed into a sphere only about 20 kilometers across, collide with each other. Supernovae can also produce gravitational waves, particularly when a massive star explodes asymmetrically as it collapses at the end of its life. In all these cases, the common factor is enormous masses moving at high speeds and changing direction rapidly, creating the disturbances in spacetime that we detect as gravitational waves. LIGO stands for Laser Interferometer Gravitational-Wave Observatory. It is a large-scale physics experiment specifically designed to detect cosmic gravitational waves. LIGO consists of two identical detectors located thousands of kilometers apart, one in Livingston, Louisiana, and the other in Hanford, Washington state. Each detector features enormous arms arranged in an L shape, with each arm stretching 4 kilometers in length. This facility is operated by the California Institute of Technology and the Massachusetts Institute of Technology, with funding from the National Science Foundation. The separation between the two detectors is crucial because it allows scientists to confirm that a signal is truly a gravitational wave and not just local noise or vibration. Both detectors must see the same signal for it to be considered a genuine detection. LIGO uses a technique called laser interferometry to detect gravitational waves. Here's how it works. A powerful laser beam is split into two parts, and each part travels down one of the detector's perpendicular arms. At the end of each arm, mirrors reflect the light back and forth hundreds of times, effectively making the arms much longer optically. The two beams then recombine and create an interference pattern. Under normal conditions, when no gravitational wave is passing through, the beams cancel each other out perfectly. However, when a gravitational wave passes through the detector, it stretches one arm while compressing the other, changing their lengths ever so slightly. This change causes the recombined beams to fall out of perfect sync, creating a detectable signal. The sensitivity required is staggering. LIGO can detect changes in arm lengths smaller than 1/10,000th the width of a proton. On September 14, 2015, LIGO made history by detecting gravitational waves for the first time. This event was designated GW150914, named for the date of detection. This momentous discovery came exactly 100 years after Einstein first predicted the existence of gravitational waves in his general theory of relativity. The detection was so clear and unambiguous that it appeared in both LIGO detectors within milliseconds of each other, confirming that the signal came from deep space rather than from any local disturbance. This breakthrough marked the beginning of gravitational wave astronomy, a completely new way of observing the universe. Scientists around the world celebrated this achievement as one of the most significant scientific discoveries of the century. The signal that LIGO detected on that historic day came from two black holes spiraling together and merging into a single black hole. The two black holes had masses of 29 and 36 times the mass of our Sun. This collision occurred approximately 1.3 billion light-years away from Earth, meaning the event happened over 1 billion years ago, and the gravitational waves have been traveling through space ever since. During the final moments of the merger, an astounding amount of energy was released. 3 entire solar masses worth of matter were converted into pure gravitational wave energy, according to Einstein's famous equation E=mc². The entire event, from the final inspiral to the merger, and the settling of the newly formed black hole, lasted just 0.2 of a second, as observed by LIGO. The first detection of gravitational waves had profound significance for physics and astronomy. Most importantly, it provided direct confirmation of Einstein's general relativity prediction made a century earlier. It also marked the first observation of a binary black hole merger, proving that such systems exist in the universe. Before this discovery, scientists had never directly observed black holes with masses greater than 25 times that of our Sun, but this detection proved they not only exist, but can merge together. The discovery was so significant that it was awarded the Nobel Prize in Physics in 2017. The prize recognized the decades of work by thousands of scientists and engineers who made this incredible achievement possible, fundamentally changing our understanding of the universe. The detection of gravitational waves has opened a completely new era in astronomy. For the first time in history, we can observe the universe through gravitational waves rather than just electromagnetic radiation like light, radio waves, or X-rays. This is revolutionary because gravitational waves reveal events that are completely invisible to traditional telescopes. They pass through dust clouds, gas, and matter that would block light, carrying information from the most extreme environments in the cosmos. This has enabled what scientists call multi-messenger astronomy, where we can observe the same event using both gravitational waves and electromagnetic signals, getting a much more complete picture. Gravitational waves truly allow us to hear the cosmos in ways never before possible, detecting the vibrations of spacetime itself and unveiling a universe that was previously hidden from our view.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.